Hi, everyone. Thanks for having us today. Um, we are going to present to you about our project, the Rwanda Institute of Conservation Agriculture, the application of earth and timber as primary structural materials. Um, yeah, I'm Cam Bailey. I'm registered with the IStructE in the UK, but also a member of the Institution of Engineers in Rwanda. I'm the Director of Engineering here at Mass Design Studio in Kigali, Rwanda. I also lead an initiative called Conservation Communities, which is in part to do with bolstering local supply chains, particularly for natural and bio-based materials. I'll hand over to Amab to introduce himself.
My name is Aimable Mukire. Aimable is a French, so there is that tweak. I'm a senior structural engineer at Mass as well. Yeah, with a focus on designing with sustainability in mind.
Thanks, Amab. So just a bit of background on Mass. We're a collective of over 130 architects, landscape architects, engineers from various backgrounds and disciplines, writers and researchers and filmmakers representing around 15 countries across the world. We're a registered nonprofit organization with a mission to research, build, and advocate for a built environment that promotes justice and human dignity. We partner with other organizations to further their mission through the built environment. We've got, as mentioned, where both Amable and I are based. We have an office in Kigali, Rwanda, where we focus on work across the African continent, along with offices in Boston, Santa Fe, New Mexico, and Poughkeepsie, New York, all in the USA, focused on projects in North America. We work with partners through the earliest stages of design, through kind of ideation of projects, understanding what a project can really be and how it can be most impactful, all the way through design and construction to project completion, where we try to demonstrate the outcomes of any specific design interventions that we've made along the way. So as mentioned, we're here to present today about the Rwanda Institute of Conservation Agriculture, otherwise known as RICA, a bit less of a mouthful. It's a new university campus established in Bugesera district in the south of Rwanda, set up to teach the principles of conservation agriculture. The campus is formed of around 70 individual buildings of varying levels of complexity, ranging from staff and student housing to enterprises where the curriculum is actually taught, to kind of more complex buildings like the campus center in the heart of the campus, which forms the kind of administrative and communal hub. The project was funded by the Howard G. Buffett Foundation and is located on a 1,500 hectare site in Bugesera district that was donated by the Rwandan government. Mass completed this design with support from Arup in the UK. In keeping with the sustainability and conservation focused ethos of the project, which I'll talk a little bit more about in a second, the structural design really aimed to be as low in embodied carbon as possible. And Amab will talk a little bit more about the specifics of embodied carbon. Across all buildings, the foundations are constructed from local stone. The walls are constructed from earth sourced from the site, and the roofs are built using regionally sourced timber trusses for the most part, but also beams, rafters, purlins, etc. The project's won a number of awards since it was completed a few years ago, including an iStructE award in 2024 that was given for holistic regenerative design. So a bit of background on why this project. The majority of Rwandans still depend on subsistence agriculture across the country. And the country is the most densely populated country in Africa and one of the most dense rural landscapes in the world. In the 1990s, the country had a healthy proportion of natural forest and grassland. However, over just 3 decades, you can see how much of this has changed, with much of the forest and grasslands remaining being kind of enclosed in national parks. Yeah, even with around 80% of the land now operating as farmland, around 20% of the population remain food insecure, and this is a growing issue as the population continues to increase. RICA's investment in innovation with sustainable agriculture is considered crucial to the country's health and wealth outcomes. So the mission of the RICA campus was to train the next generation of leaders in conservation agriculture to attain healthy and sustainable food independence in Rwanda. So here we asked, how do you best balance conservation practices, agriculture practices, community well-being, along with local material sourcing and carbon positivity at scale? So we mobilized this through what we call a One Health approach. So our landscape team first observed the campus to identify key ecosystems that were important to preserve. A vast portion of the 1,500 hectares contains one of the last remnants of savanna forest in Rwanda, outside of the Akagera National Park. While the papyrus wetland along the lake shore at the bottom of the hill is a hotspot for biodiversity and also an important material source for local craftspeople. We protected these areas of the site and located all buildings on the campus in the space between. We also located buildings based on soil quality and growing conditions, with more arable land at the bottom of the site being used for crop-based curriculum, such as row and forage and veg and tree, and the first year farms, where first year students kind of really learn the processes of agriculture, hands-on agriculture. While the upper portion of the site was used for animal grazing, supported by enterprises such as the dairy and the poultry and swine. I think I just skipped over a slide, so I'll just jump back one. This idea of One Health is the idea that a human settlement can be productive and beneficial for the environment in which it is built, and the idea that the well-being of humans, animals, and ecosystems are all very much intertwined. So in terms of the infrastructure for the campus, we're in quite a remote location here, kind of quite far from the closest village. So we mobilized the lakeshore location to achieve circular water systems and installed a large solar farm at the top of the site to provide power to the entire campus. This made RICA 100% off-grid with renewable power and water systems in place. So as we get into structural design, the key issue is obviously resilience. Given Rwanda's proximity to the East African Rift System, it is one of the more seismic regions on the continent, particularly in the west of the country. Earth construction is renownedly low in strength, it's quite brittle and heavyweight, and so not ideal for seismic scenarios. But we thought we would give it a go anyway, particularly as we were based more in the southeast of the country, where we do have slightly lower seismic hazards, and we designed the buildings for a peak ground acceleration of 1.6 meters per second squared, or 0.16 G. And in terms of the design that we followed, Rwanda building code is in place, and it does require seismic design, but there aren't any Rwandan standards currently in place to follow for seismic design. So we learned very heavily on the Eurocodes, and then partnered this with the New Zealand standards, which cover earth construction quite well. And so I'll hand over to Aimable at this point to talk about the walls and the earth.
Thank you, Cam. We'll move into the earth section and go through our process into using earth as a welding material at the entirety of all the walls on this project. So to start, you would ask yourself, why earth? So we do know that in general, the building industry does contribute to a large portion of the global emissions, and 11% is from the construction industry itself. And that means materials and how these materials are manufactured or produced and where they are sourced. And we thought that earth could be a good alternative material compared to conventional materials, which is not typically used on a project of this scale, especially in Rwanda. And to start, we looked into materials that are typically used in Rwanda. So looking into concrete and fire bricks. And for instance, we know that fire bricks does require higher energy during combustion and can sometimes often lead to deforestation if it is not done sustainably. And we also do know that CMUs that require some amount of cement. And these are the materials that we quite wanted to divert from at the start. And contextually as well, this earth made a lot of sense to be used because the skills already exist, the materials is available and plentiful in Rwanda, and there is no need for any infrastructure for this material. But historically in Rwanda, a huge proportion of Rwandan homes are built using earth, and it is often associated with low-income housing and poor quality homes, and can sometimes be dangerous based on how these are built. And we also know that it does reduce the reliance on high energy materials like cement, and it does help regulate the indoor temperatures naturally and can overall reduce the environmental impact of the buildings. And just beyond the performance, it does also connect to the local building traditions and the skills that are available locally, making it both practical and scalable. But based due to the poor workmanship and poor quality of earthen homes in Rwanda, it was banned until 2022. Banned by that I mean restricted by the building code. And our first question was to whether we can design using earth buildings that are sustainable, durable, breathable, but most importantly, resilient to moderate seismicity. And this was an opportunity to see if we can change the local perspective. And to embark on that journey, we started with a feasibility study, first to understand whether the use of this material on this project is possible. And we went into literature to understand what has been done historically, to understand what is the base soil that will give us better results. And on this site particularly, we had the luxury of having different areas that we could source soil from. And we had 4 locations with varying types of soil, so ranging from either sandy to clay soils, which we therefore collected, and we designed different mixes. For the mixes, we taste samples using either stabilization of cement and lime, and samples with no stabilization at all. And we did taste about 5% to 7%. In the end, we did realize that with 5%, we could get almost all the properties that we wanted, but we were not achieving the protection that is required, especially during construction. So we upped the stabilization using cement up to 7%. But even with that, with 7% cement stabilization CACBs, we still had a 73% reduction compared to a fired brick. And whilst producing these CACBs, we also, from literature view, we developed quite a number of low-tech testing that could be done by the personnel producing the bricks to understand things like optimal moisture content and the plasticity of the soil to be placed so that we get better results and better bricks in general. And we moved to laboratory testing, and this was a test that we could benchmark with the performance requirements from the Eurocodes or other standards that we used. So that included things like compressive strength, water absorption, to understand, to give us design data for our design. Yeah, and these are also the targets or the requirements that we had established from um, from the codes. For instance, we are looking the compressive strength to be 11 PA or the water absorption to be between 10 to 15%, which is also in line with other masonry construction materials. And we had challenges. We did develop a tasting, but we could only get so far with the facilities available in Rwanda. But one of the challenges that I could say was in regards to the Young's modulus, which we had to make the assumptions because whereas on other materials, they could be change if, for instance, on Earth, there was no adjustment based either on soil type or stabilization used and density of Earth. And given that Earth is highly variable, it was quite, we didn't find any guidance or any structural guidance that we could use to adjust these properties. And this was a problem that could lead into a bit of conservative design. And now moving into the design and detailing, one of the key areas that we understood is to design buildings for durability. And this meant either providing a concrete print, which was about 150 mm raised from the floor finish level, and providing quite roof overhangs and window sills as well, just to make sure that the water is not affecting the walls. And in general, we had two typologies of the buildings. One that was residential buildings and enterprises buildings. And I will go into more details, but our intent was to use unreinforced earth for residential buildings. The aspiration was to make these residential buildings as sustainable as possible, but still designing them for moderate seismicity and breathability. Just because residential buildings were inherently risk vulnerable than larger enterprises buildings to the seismic hazard because they are single story, they had higher wall density. So we thought this could be reinforced. And in terms of the overall structure, we used stone masonry as a foundation, CSCB's walling, and timber ring beam, and timber diaphragm. But even though our intent was to make these unreinforced, we still, in practice, had to provide tie down rebars to combat overturnings at both ends of the panels, and shear that was either at the base to connect the walls to the grade beams, and at the top where these walls meet the timber ring beams. And on average, even though these walls were said to be unreinforced, they ended up using about a quarter of steel reinforcement of reinforced walls. One thing that we've learned, even though from lots of engineering guidance that we reviewed, recommended using timber ring beams. In reality, this involved a lot of complex connection, and it was quite difficult to resolve on site. And you can see from these images, different systems that to be coordinated, especially where we have reinforcement and how the timber rafters were connected on the ring beams. And the next typology of buildings were enterprise buildings, which were typically 2 stories and are more likely vulnerable compared to the residential buildings. And they had taller walls, larger spans, and less density of the walls because of the open spaces. And it was clear from the start that this has to be reinforced walls. And in contrary to the residential building, we used concrete ring beams, and we also used steel cross bracing as a diaphragm just at the underside of timber trusses. But all of this, we had learnings as in key areas uh, to keep in mind while designing this building, especially for reinforced. Things like coordinations, which was quite key on how the reinforcement would run into the whole hollow parts of the blocks from the grade beam to the ring beams, and where this lap would happen. And to get back to the question that we had when we started this, whether we would be able to design a sustainable, safe and sustainable buildings for moderate seismicity, we could say it's possible, but of course with a few reflections. One is preparation and quality control is quite essential, especially because of the variability of earth as a construction material. On site, we produced 2.5 million CCB blocks, and storage, they are prone to rain that would degrade their capacity or their quality. So either preparation was quite essential to the success of this project, and as well the detail of durability by protecting especially uh, from water. And we also felt a bit constrained by the lack of data. So in different areas, we had to combine codes, but most importantly, there was a lack of data that recognizes the variability of the material that leads to a conservative design. And even though the stabilization of the CACB can significantly impact the material properties, the team did find that the available guidance would often give a single value of a material property, and that it would not necessarily indicate whether this applies to a stabilized or unstabilized earth. And this stands in contrary to other construction materials such as concrete or timber that often recognizes different strength and stiffness or grades of these materials. But overall, we could say that this was a success. On this project, we did design one and two-story buildings to follow the seismic principles with Earth, and the required level of reinforcement basically vary depending on the wall density and the number of stories. With that, I will give the floor back to Cam to talk about timber. Cam, you are on mute if you are saying anything.
Sorry about that.
Mm.
I just dive straight in. Yeah, so as mentioned, we decided to mobilize timber as another primary structural material in combination with the earthen walls of the buildings, as another kind of natural bio-based material in order to reduce the embodied carbon of the structures. And actually, the beginning of this project, when the project was first kind of being ideated, it aligned very closely with the opening of Rwanda's first FSC certified forest called New Forests in the south of the country, close to Nyungwe. So we thought it would be a great opportunity with the number of buildings included to kind of use this as a demonstration project for regionally sourced timber. Um, and Yeah, I mean, typically the issues with sourcing local timber is that the timber is generally sourced in a kind of informal way, and it's more often sold for charcoal or temporary scaffolding than for permanent timber structures. And so yeah, as I say, the project was inspired by this new mill opening up. They'd purchased kilns and milling equipment just around the time the project was starting up. However, because the forest was quite new, and this is the case for many forests we see in East Africa, is that they've only recently started being managed. And so many of the mature trees contain quite a lot of branches and perhaps aren't as straight as you might otherwise expect. And so this can lead to extensive knots and defects in this timber. And with the growing period being around, 10 to 20 years for softwood, we needed to use this kind of already mature material. And I think just a point to note is the predominant tree species grown in Rwanda on a kind of larger scale include eucalyptus and a species of pine called Pinus patula, neither of which are native to Rwanda. However, the eucalyptus is very disruptive to its local environment. It's very water intensive, and you'll see often the eucalyptus plantations don't have much kind of undergrowth, and they're not very good at sustaining the local biodiversity because they're so nutrient demanding. And so we chose to use Pinus patula on this project because, whilst not native, it does allow other species to grow below it and can be used in kind of buffer zones around natural national parks that do have native species growing within them. But another issue as well is the issue of treatment. It was quite uncommon to see properly treated timber in the region. And because we want these buildings to last for 50 years or more in a tropical environment where we're surrounded by termites and other boring insects, the treatment is a really important part of using this material. So unfortunately, the main form of timber treatment on mills that do exist in East Africa is based around the use of eucalyptus being used for telephone poles, which are often in quite harsh, abrasive environments, very exposed. And so CCA treatment is used, standing for chromated copper arsenate. As the name suggests, the product contains arsenic. And so it's actually, this type of treatment is actually banned in many parts of the world, including Europe and the US. Uh, and as the mills have to go an extra mile to ensure workers' health is protected when using this type of treatment. And so actually other countries prioritize treatment methods like ACQ, which has similar results, but it's less harmful. The other issue with CCA treatment at the other end of the project is the offcuts can't be burnt because when they're burnt, they release these pathogens. And so we need to bury the waste in lined pits, well away from watercourses, in yeah, kind of well-planned landfill. But this does cause environmental risk and compromises the argument to use timber in the first place, to be a more sustainable alternative to other construction materials like steel, for example. And we do hope to kind of push, and there are many people pushing towards the kind of transfer from away from CCA treatment in East Africa and move towards a more safer treatment method. And finally, another issue is grading of the material. With the mills in East Africa being relatively new, there's no timber grading capacity that really exists, and there's no regional timber grading standard. So upfront, for the purposes of design, we assumed a kind of S7 equivalent grade according to SANS, which is similar in ways to the C16 grade that we see in Europe. This was considered quite conservative, based on the research that we've done for the species, in particular Pinus patula. The density of this pine is quite high, and so we'd aligned it based on advice from experts and our own research. Yeah, on this kind of S7 grade. And we also made the assumption that the timber we could get once we were up and running would meet visual grading requirements to demonstrate that we could achieve this S7 grade. There's two methods of grading that we can use. There's visual grading and mechanical grading. We're very aware that mechanical grading wasn't an option because of the mills being very new. And so we thought we'd lean very heavily on the visual grading. So they were our kind of upfront research and assumptions and challenges. So going back to New Forests, this Rwandan timber mill, their kiln could only fit 4-meter lengths of timber in it. And so actually we designed almost every building across the campus based on this length of timber in order to minimize those offcuts that would have to go to landfill. And so the structural grid of the vast majority of buildings are 4 meters by 8 meters, based on the kind of 4-meter purlin span, and then the trusses being able to be made out of 2 lengths with steel connections at the nodes. It was also, this worked in our benefit because the project was very, very fast moving. We didn't have a huge amount of time to design quite a large number of buildings. And so utilizing this kind of modular approach benefited us in terms of design time frame, with the truss that became known as TT1 being used across many of the buildings. And the original intention was to source all 3,000 cubic meters of the timber required for the project from New Forests in Rwanda, only 200 kilometers from the site. However, once the project started construction, New Forest had some issues meeting the demand, and the first phase of the project was really time critical, with first-year students waiting to arrive in July 2019. New Forest ended up being able to deliver around 25% of the timber required at the level of specification that we needed to reach this S7 equivalent grade and within the time that we needed it. And so we were left looking for other sources. Um, because the supply chain is limited within the region, we were looking quite far afield to other major timber suppliers just in order to meet the demands that we needed. But obviously, this would be offsetting some of the carbon savings that we're making through using timber and almost made that decision obsolete just through the carbon produced through transportation of large volumes of material. But yeah, we looked at Canada, Northern Europe, Turkey, India, and Sri Lanka, and of course South Africa being our kind of closest option. However, through some in-depth research and some visits, we were able to find enough mills to source the timber from in Rwanda, Uganda, and Tanzania. So we went from a kind of 200-kilometer delivery distance to a maximum of 1,400 kilometers. I think the furthest was in Tanzania. But with all of these mills, again, as I say, the grading capacity is limited, and we don't have a regional grading standard. And so we mobilized visual grading, as I mentioned earlier, but we had to do a lot of training with the contractor and their workers on how to do visual grading. In fact, both with the contractor and with the mills. And the mills became a little bit resistant to kind of doing all this work up front. So we ended up ordering timber in bulk and then grading it after purchase. However, trying to meet the grades required to achieve S7 or C16, we had huge rejection rates with all of the timber. So we decided to adjust our specification for visual grading and create our own grades ourselves, and then demonstrate the strength through testing of samples from each batch of timber delivered. And as I mentioned, the main issue was just the quantity of knots. And it was very hard to reject timber as well because it had already been treated with CCA and there wasn't much use for it otherwise. And so we really wanted to use as much of the timber as possible. So we developed nice, clean testing plans in accordance with the Eurocodes, with the hope of one of the mills purchasing, or the contractor even purchasing some testing equipment to do this work in a nice monitored and closely aligned way with the method stated. However, no one was really up for doing that, and so we ended up adapting a concrete cube crushing machine using just welded steel bars to create the 4-point bending test. That is the kind of main way of testing strength according to the Eurocodes. It's important to note, whilst there are a number of tests that we could do, we, in the essence of time, given that construction was happening at this point, we decided to limit to bending tests where we could also get the modulus of elasticity as well as the bending strength, and also measure the density. And within that, there are methods within Eurocodes to convert that to a kind of equivalent C grade to determine your compressive strength parallel to the grain, tension strength parallel to the grain, etc. We tested around 40 specimens, full-size specimens per batch of timber that was received on site. I think we ended up with around 15 batches with roughly 40 samples being tested from the various mills. And so you can imagine it was a huge log of data to keep track of. And of course, with timber design, given it's a natural material that grows in variable ways, we can't just use the mean or the average value. We have to use the 5th percentile value or the characteristic properties of the timber to ensure that 95% of specimens or of the timber being used across the project are above the strength value used in design. And so we crunched a lot of numbers. We removed outliers from the data sets. and we carried out a lot of statistical analysis on these sample batches to determine the values we could use in design. Um, so in terms of density, and just to explain here, the kind of pink box and whisker diagrams you can see on the slide here are what we call grade one. So timbers that didn't meet the S7 visual grading, but met our kind of slightly higher, less knots, less defects type grade. And this was meant to be our kind of best timber. The blue represents what we call grade two, which was slightly more knots allowed, intended for less critical elements in the structure. And then finally, the yellow being timbers that didn't meet any of the grade, but we thought we'd test them anyway to see if we could use them. And so, as you can see here, the density actually came out pretty consistent across all batches and all grades. Roughly around 500 to 550 kilograms per meter cubed, which is high for a softwood, and again backs up why we thought the timber might be a bit stronger than it was. But as you'll see, if I go to bending strength first, the bending strength we got again were relatively consistent again across grade one and grade two, but less so against the kind of ungraded timbers. But when we worked out our characteristic values, because of the large spread we saw in the results, we ended up getting basically 10 to 12 MPa or megapascal bending strength, characteristic bending strength that we were allowed to use. Then in terms of the modulus of elasticity, we saw quite a lot of variance in the batches. And the stiffness properties are significantly lower than we would have hoped or would have expected with similarly dense timbers grown elsewhere. And so we were getting a kind of mean modulus of elasticity of not much more than 4,000 MPa, if that, and characteristic values of around 2,500 or 3,000, which is around half of what you might expect from a C16 grade or S7. We think this is due to the speed at which the timber grows, but some more research is needed there. And so what that meant is, whilst the buildings were being built, we had to decide where these different grades of timber could be used and applied across the structures. So as I mentioned, less critical elements mobilized the weaker timbers, and top and bottom chords of trusses, we specified the higher grade of timbers. And so there was a huge amount of organization that had to happen on site from our supervision team working with the contractor to ensure these things get done properly. However, after all of the effort and the hardships in the process, just to touch on some of the outcomes, we were able to source around 96% of materials by weight within Rwanda. I mean, obviously, a lot of the weight comes from the earthen walls. This all came from the site, but I think this number even includes kind of the furniture that goes into the buildings, etc., where we used mass also designed through our furniture team, utilizing locally sourced timber and papyrus, etc. We worked with a large labor force of kind of 2,000 plus people, or even more perhaps, 98% of which came from within 100 miles of the site. And a large proportion of these workers were trained in formalizing earth and timber construction. And actually, there's stories of kind of break-off groups from the contractor going on and setting up specialist contracting firms in earth construction, and they've gone on to build kind of lodges and other things in the country using these materials. Compared to the business as usual, where you might expect to use kind of metal roof sheeting, steel trusses, installing a suspended ceiling, perhaps using concrete block walls and concrete foundations, we were able to demonstrate a nearly 60% reduction in upfront embodied carbon. The stages A1 to A3 is kind of known as cradle to gate to get the materials on site. By stripping back and using these natural, locally sourced materials. Around 2/5 of the global average for educational buildings. Whilst these materials aren't particularly innovative and both have been used for hundreds, if not thousands of years for construction, formalizing it in a way where we can achieve these kind of modern buildings that are resilient to earthquakes was an important step in this project. We also calculated our carbon metrics for the campus as a whole, including upfront embodied carbon, operational carbon, leaning back on the 100% off-grid energy and water systems, plus a lot of the biodiversity restoration that our landscape team designed along those natural ecosystems and within the campus itself, which sequester carbon well within the campus. And through all of this, we've been able to demonstrate that RICA is likely to become the first carbon positive university campus in the world by around 2035. Now, if we've got time, I do have a short video just to present that our media team has put together. Hopefully you can all see the screen here. Let me just stop sharing and make sure that I have. Hopefully this comes through.
Architecture has made great strides.
At the same time, our planet, our health, and the ecologies we depend on continue to suffer.
Regeneration is required, and it requires us to rethink how we design.
It requires us as architects, engineers, and landscape designers to work together beyond buildings. On the shores of these Nile-bound lakes, Kilimbi and Gahargwa, the Rwanda Institute for Conservation Agriculture, RICA, is solving part of our shared global problem, providing healthy food and shared prosperity on less land for more people and an increasingly fragile environment. A One Health education is preparing the next generation of conservation agriculture entrepreneurs
to overcome these challenges. The landscape began to form a map to expand one of Rwanda's last savanna woodlands
with macadamia and these acacias that these gray-crowned cranes rely on to prosper and prevent disease.
Building sites began to create harmony between agriculture and conservation.
Soil health, grazing and growing alongside filtration, planting and pollinating.
This place provided a map for how to build.
Rammed earth and earthen blocks elevated human handprints while lowering carbon footprints, as did timber, harvested and reforested. This campus was not only born of blocks and beams, it was born of care, quality, and commitment. Only through a collective, accompanying community,
could we discover a new way to build
and greater hope for us,
the animals,
and the environment we all depend on.
Great, thank you. And yeah, that's the end of our presentation. Thank you very much for having us.